domestication, humans have been changing the genetic makeup of organisms since the origins of agriculture. Domestication of plants and animals involved selection to promote some traits and eliminate others. In some species, the results have been dramatic, as in the evolution of wheat. In the thousands of years since domestication began, humans have produced a world of agriculture, horticulture, and plantation forestry by manipulating genes and genomes, most commonly through selection. Synthesis of information gained from genetics and archaeology is a promising approach to further our understanding of how selection acted during domestication of plants. From such studies, we know that humans at the hunter gatherer stage of their evolution cultivated food plants in 24 different locations independently. So, energies formerly expanded in finding food were directed into methods of agriculture. Although originally developed in the Middle East, China, and Central Africa, such changes spread rapidly. Within 100 years or so, some form of agriculture had begun in many contiguous areas. The most immediate and the most far-reaching effect of agriculture was to increase food supply manyfold, a change permitting larger populations and a greater population density in agricultural communities. What matters here is the change in human lifestyle. Although there are uncertainties concerning whether sedentary communities preceded or followed agriculture and whether agriculture was stimulated by climatic changes or by directed Neolithic solid social complexities. It did not take many generations for humans to settle arable areas on a permanent basis. So grasses from which cereal crops arose were cultivated in half these locations. Loss of seed shattering, dispersal before harvest, and an increase in seed size were early and adaptive response of plants to selection associated with the domestication. Adaptive changes in seed size were rapid, as little as 500 years for rye. Small number of genes were sufficient to reduce an seed scattering, that is, selection on a few regions of the genome is sufficient to drive domestication. Phenotypic variation in domesticated strains can exceed the amount of variation in the undomesticated wild ancestors. In agriculture, it has been standard practice for millennia to develop new varieties through hybridization between different species. At first, the species concerned were closely related. By the middle of the 20th century, however, methods had been developed that allowed crosses between more distantly related species. For example, triticale, a widely grown cereal, is a hybrid between wheat, triticum, and rye. The Green Revolution, a series of research, development, and technology programs aimed at increasing global agricultural production, was a major achievement of this type of breeding. Yet, although intended to alleviate starvation and property strike in regions, the Green Revolution drew a great deal of protest for its environmental and social consequences. The ethics and safety of gene transfer between species were not, however, raised as areas of concern as they have been with genetic engineering, the subject for the next section we will be learning. And developed after the Green Revolution, the genes transformed in this relatively new technology often come from a different phylum or even kingdom, which was not the case with earlier breeding practices. Then genetic engineering of food crops and animals. The early 1970s marked the beginning of the era of genetic engineering when it was discovered that DNA fragments from different sources could be spliced together to form entirely new recombinant DNA, which could be used to introduce new traits to the organism. A basic technique of genetic engineering is to insert a new or modified nucleic acid sequence into a virus or plasmid that can carry these novel sequences into host cells and enhance host genomes where they can be incorporated and amplified many times over. This technology allows active intervention into the genetic material of any organism. Genomes of many organisms have been manipulated to affect such traits as protein production, resistance to infected areas, agricultural yield, nutritional value, toxic susceptibility, environmental stamina, tumor resistance, and so forth. Such multiplication of genetic traits allows us to move organism evolution from the age-old province of random mutation and natural selection to human-directed evolution. Genetic engineering is now big business, especially when it comes to agriculture. The first genetically modified organism, the flavor saver tomato was put on the United States market in 1994. Although the flavors never failed on the market. The production was ceased in 1997, little more than a decade later. The area covered by just the four major genetically modified crops in the United States, corn, soybean, cotton, and canola, had grown to many, according to 2006 US Department of Agricultural Statistics. A large proportion of food in North America supermarket shelves now contains at least some genetically modified content. The area under cultivation of GM crops continued to escalate. By 2009, it had grown to encompass 35 4 million kilometers worldwide. A major exception to this trend is Europe, where a huge public outcry against the technology on ethical, environmental, and food safety grounds continue to have an impact on government policy. With their early emphasis on increased resistance to insect pests, diseases, and herbicides, the most common GM crops in use today were largely developed with financial profit in mind, but the potential is enormous. Improved nutrition, golden rice, for example, is rich in beta carotene, provitamin A, is one such promised benefit. Other benefits may exist as well, as documented over more than a decade. Transgenic corn can reduce pest damage, and non genetically engineered corn or maize in adjacent fields. GM technology has been applied in many other organisms beside plants, including fish for enhancing growth, cold tolerance, and human insulin production, cows to produce human growth hormone and casein enriched milk, pigs for lowest fat content, and mice to produce fish oils. Although most of this work has yet to be approved for commercial application, in 2006, approval for release of a train of the first pharmaceutical drug generated in a mammal, a goat, was granted in Europe. Indeed, the pharmaceutical industry is investing heavily in research into this method of drug production. So, microorganisms have been used to produce a wide array of human and other proteins, for example, human growth hormones, and an essential blood clotting factor for hemophilia sufferers. So, how this is done? A general scheme for constructing a clone of recombinant DNA molecule using plasmids and restriction nuclease enzyme, a foreign DNA molecule, human insulin, and a plasmid vector are selected, both carrying recognition sites that can be cleaved by a restriction enzyme. Cleavage produces one or more fragments of the foreign DNA and opens the plasmid vector along the DNA to be inserted. Plasmid carrying the foreign DNA is inserted into the host cell, in this example into the bacterium E. coli. Because some bacteria fail to take up the plasmid, the cells are screened for the presence of recombinant plasmids, a process that may involve growing the cells in the presence of specific molecules, tetracycline or ampicillin in this example. Clones carrying the genes of interest are further replicated to obtain large quantities of genes. Obtain plasmid and insulin gene, plasmid cloning vector, human DNA genome, insulin gene, then just sticky ends are there, cut DNA with restriction enzyme, mix gene with cut plasmids, add DNA ligase. Later, some plasmids fail to incorporate gene, some just take up the new gene part. Plasmids put into bacterial cells by transformation. Bacterial chromosomes are there, some bacteria fail to take up plasmids. Screen for recombinant plasmids. Clone bacterial colony, then master plate, growth medium tetracycline, growth medium plus ampicillin. Clones carrying insulin gene, identify and isolate clones carrying insulin gene. So, in summary, the major benefits conferring by GM technology are that, in contrast to more traditional breeding techniques, which are time consuming and inexact, GM is more efficient, more precise in its choice of genes, and allows genes from a far wider range of organisms to be introduced into a recipient's organism's genome. When combined with cloning, its scope may be further enhanced. Some major concerns about GM technology. The physical or biological environment considered natural is not unchanging. Organisms have regularly affected and changed the environment and continue to do so, while humans have long engaged in succession of inventions into nature that have changed it from its form, function, and substance in most localities and for many organisms. An important feature of GM technology is that the genes employed usually come from a species other than the receiving organism. To many, this poses a substantial ethical problem, but gene flow via horizontal gene transfer between organisms is a common event across the new tree of life. Species barriers are continuously being crossed by viruses, transposons, and plasmids, all of which can carry genes from one species to another. Humans readily incorporate genes introduced by viruses through though, but not by bacteria. The latter was, however, controversial for a time. Human genomes contain many hundreds of transposable elements that affect gene expression, genetic recombination, and unequal closing over of chromosomes, some of which entered the genomes of human ancestors 4 million years ago. Environmental concerns about GM crops are mostly focused on the perceived threats to local biodiversity and ecosystems. In, in particular, the possibility that pollen from GM plants will fertilize closely related wheat, a problem if the crop is modified to resist pests or herbicides. Closely related native plants whose very existence might then be threatened, or non-GM crops of the same species. The long-term impact of such clauses will depend, of course, on the relative fitness of the genes in question. Again, this is not a new thing. Gene flow from crops altered by GM methods has occurred for many decades. Nevertheless, great care can be taken before introducing any new GM crop. After that, our experience with the technology is still relatively limited, and long-term effects can be difficult to identify. Next major topic is about our influence on the evolution of other species and their environments. Humans have had extraordinary impacts on the distribution and gene pools of organisms they have domesticated, and on organisms where the impact was more indirect. As aptly summarized at the beginning of the 21st century, technological impact has increased so markedly over the past few decades that humans may be the world's dominant evolutionary force. In the same paper, Plum by estimated that annual economic cost to the United States of human induced evolution of insect pests and new drugs against drug resistance, streptococcus virus and HIV as $50 billion. This figure doubles when other organisms are taken into account. So, starting in the Paleolithic, and human actions such as hunting or the widespread use of fire may have led to the extinction of megafaunas of Australia, the Africas, and other parts of the world. Humans have altered both the species mix and environment of almost the entire globe. A notable example today is the plight of the oceanic fish stocks, all of which are under threat from overfishing. Despite a moratorium on fishing and other conservation measures, populations of the northern coast of Newfoundland and Labrador have not recovered at all from a destroyed collapse in the early 1990s. Whereas humans have moved, especially since the development of agriculture, they have brought with them a variety of other organisms, both domesticated cattle, goat, and opportunistic rats, weeds, disease causing microbes. Changes wrought on local environments took a quantum leap when Europeans began venturing across oceans. Impacts on native humans was newly discovered. Regions were calamitous, a story told by Gerald Diamond. In the decades following the arrival of Europeans in the Americas and the Pacific, infectious diseases such as smallpox, measles, and tuberculosis decimated indigenous human populations that up till then had been isolated. A similar fate befell a variety of animal and plant species, especially trees, for example, the American chestnut, which was devastated by a fungal blight apparently imported from China or Japan in the early 1990s. Among the effects have been mass extinctions, especially on islands. Hawaii is a prime example, and displacement of native species by invasive weedy ones. The list is long, fueled by globalization. Such impacts continue today. Agents of destruction can arrive from any quarter. Invasive species carried in the ballast water or ships, or insect pests carried on lumber. Two examples: entire ecosystems are threatened, or in some cases have disappeared. So these imparts on other species and ecosystems threaten human themselves. Another book, Collapse: How Societies Choose to Fail or Succeed. Later Diamond details the consequences of succeeding exceeding our resource base. Using a number of case studies, he shows how human societies in different times and places have collapsed as a result of changes in their environment. Such changes were in large part participated through their own actions, including faulty agricultural practices, deforestation, and water depletion, to name a few. Today, our resource base is the whole world, and our impacts are accordingly global, extending even to climate change. The exploding human population has the potential to affect all organisms on Earth, especially with the rapidly growing ability of humans to engineer the gene pool of other organisms to create genetically modified organisms. So, with the help of this chapter, we learned some major points related to agriculture, birth defects, laboratories, alleles, domestication, ecological footprint, some about eugenics, gene therapy, genetically modified organisms, genetic engineering, human directed evolution, and negative eugenics, population explosion, positive eugenics, post reproductive longevity, recombinant DNA, reproductive technology, and selective breeding. These are the major key terms which we just learned with the help of previous and this video. Okay, so next major topic is about culture, religion, and evolution. An important part of human culture is a system of beliefs by which individuals order their lives. Many human cultures have developed belief systems in which the universe follows a designed order established by an intelligent deity. For some, the discovery that Earth is not the center of the universe made them question the necessity of a deity. So, discovery of physical mechanisms that govern the universe made others question the necessity of a creator or designer. Darwin's theory of evolution provided a natural explanation and a testable mechanism for organismal origins, relationships, and change. The realization that organisms with a heritable system could adapt their form and function to an environment, coupled with their ability to respond to changing circumstances, provided an explanation beyond the design of a creator. The replacement of a creator or designer by a process of chance and necessity produced tensions within individuals, exhibited religions and societies. Nevertheless, religious beliefs and scientific rationality coexist in many individuals and in many sections of societies. That said, it is important to remember that religious arguments have explanatory power with respect to belief systems, but they are not scientific explanations and should not be confused with or regarded as scientific explanations. Belief, religion, and spirituality. We begin with chapter begins by exploring science in relation to culture and how this theory of evolution impacted on very specific aspect of human culture system of belief. We examine the roots of religion in a historical context, how the theory of evolution impacted on religion, and how creationists view evolution. The later present especially difficult problems. Creation operates from the top down and requires faith in the existence of a superior being. Natural selection operates from the bottom up, following processes that can be analyzed scientifically. We distinguish religious beliefs from spirituality, by which we mean aspects of human lifestyle and experience such as meditation, love of music, or appreciation of beauty that go beyond a material view of the universe. There is no necessary connection between spirituality and religion or religious belief. So, science and society, as is true of any human activity, science is not independent of the society in which it is carried out. As is true of any human activity, science is not independent of the society in which it is carried out. The social context of science is amply illustrated when we consider that many regard the invention of gunpowder, the compass, and the printing press in Europe between 900 and 1500 AD as setting up the transformation of Europe during the scientific revolution in the 70th century. Francis Bacon, and the philosopher, statesman, and said knowledge is power, comes from one of his essays whose promotion of the scientific method set the stage of a scientific revolution. So the scientific revolution is based on printing, gunpowder, and the compass. The three have changed the whole phase and state of things throughout the world. The first in literature, and second in warfare, and third in navigation were have followed innumerable changes, and so much that no impaired, no set or no star seems to have exerted greater power and influence on human affairs than these mechanical discoveries. From a social point of view, the development of evolutionary theory in Europe in the late 19th century coincided with an all pervasive political and economic evolution in social behavior. Economic change posed by capitalism and its new wealthy classes allowed even encouraged European science to flourish by presenting ideological challenges to the prevailing religious and philosophical systems that had supported the old social order. To these challenges were social Darwinism and the rise of eugenics, which we just learned with the help of videos in this playlist. So, the impact of Darwin's theory on all aspects of Victorian and subsequent societies was profound. By proposing that the form and function of living organisms did not arise by creation but rather by natural processes, Darwin made it clear that species were not fixed and unchangeable. These radical ideas, which revolutionized biology, also affected sociology, anthropology, economics, politics, women's rights, fiction, poetry, linguistics, philosophy, and psychology. To quote the philosopher and education reformer John Dewey. Next, laws of nature. For many centuries, the traditional Western religious rationale for social, cultural, and biological systems was that the universe followed a designed order established by an intelligent deity. Along with the belief in God who created and maintained the universe, religion provided a set of ethical and moral values upon which to base social systems until Copernicus and Galileo in the 16th century, no one had seriously challenged the geocentric universe championed by the church. And a new world view accepted by some after the discoveries of Copernicus, Galileo, and others. The God was an initial creator who established the laws of nature, promoting the running of the universe. Advent of Darwinism posed threats to Western religion by suggesting that humans had no special place in the universe and that their origin, features, and relationships to the great apes could be explained by natural selection without the intervention of God. The Darwinian view that evolution is a historical process, extant organisms were not created spontaneously but formed in a succession of past events as organisms adapted to changing environments, contradicted the common religious view of design by an intelligent creator. Given the great age of Earth and the power of natural selection, complex designs that seem unlikely as singular spontaneous events and previously only explained as the intent of an intelligent marker, some evolutionary probable events. Consequently, for many, the reality of evolution challenged beliefs in a god or gods. The question of design. The first scientific significant, scientific, not scientific, significant cracks in the theological armor of divine intervention in nature arose through the discoveries of Copernicus, Galileo, and Kepler of natural laws regulating the motion of the solar system. Their genus was that all three provide simpler and more universal explanations of the workings of physical universe than previously available. The elegance of their explanations made inevitable and rise of science and of scientific method. The openings were widened considerably by the mechanistic explanations proposed by Isaac Newton to describe the solar system's motion through the force of gravity. Later, geologists such as Charles Lyell extended this mechanistic approach by proposing how natural forces could mold its surface. Although the scholars were not, you know, athletes, their findings about natural processes made through sciences such as mechanics, optics, and chemistry helped like gold from a continuously actor intervening agent to a prime force, a master artisan who designed logical self-functioning machines and so led to a closer examination of the nature of God. William Paley and design. The essential belief that each design has a greater purpose of is reflected in the doctrine expounded by William Paley in English an English theologian, philosopher, and advocate of Christian ethics. Pele's philosophy that Earth is the creatures were created, designed, and maintained by God is elaborated in considerable detail by his past book Natural Theology, Evidences of the Existence and Attributes of Deity. According to Paley, there cannot be design without a designer, order without choice, arrangement without anything capable of arranging, arrangement, deposition of parts, subservience of means to an end, relation of instruments to use, simply the patience of intelligence and mind. Paley's knowledge of natural history was profound. A large number of diverse and hard to understand examples of organs are discussed in depth in his book, from air bladder of fish to the elephant trunk and spider's webs. The trias formed an essential part of the teaching of natural theology of Oxford and Cambridge until the mid 1850s. Darwin studied Paley while at Cambridge, as much influenced by natural theology, and credited his knowledge of Paley's writing in helping him to do well in his BA examinations. That is what Darwin had to say. In order to pass the BA examination, it was also necessary to get a Paley's evidences of Christianity and his moral philosophy. This was done through a manner. I am convinced that I could be written out the whole of evidence at perfect correctness, but not, of course, in the clear language of Paley. The logic of this book, and as I may add, his natural theology gave me such delight as I did so careful study of these works without attempting to learn any part or wrote. It was the only part of academical course which I was then felt I was still believe was the least used to me in the education of my mind. I did not at that time trouble myself about Paley's promises, and taking these I trust I was charmed and convinced by the long line of argumentation. By answering well the examination questions in Paley, by doing this scores well and not failing miserably in classics, I gained a good place among the crowd of men who did not go in for honors. Oddly enough, I cannot remember how high I stood, and my memory fluctuates between the fifth, 10th, or 20th name on the list. Simple common sense seemed to support supernatural design. Organismal design presuppose a designer who, by definition, but not based on any scientific evidence, is an intelligent supernatural being, a chain of reasoning that led back to creation and a creator. Paley began his book with the most famous example and question concerning design and designer. Can there be a watch without a watchmaker? And by tension, can there be a person without a person maker? Laws without a lawmaker. Paley used his analogy to illustrate his convention that humans could not exist without a creator. Indeed, it is not surprised to find a creator story in the history of many cultures and societies. Evolutionary theory, the essential challenges that religion poses has become been how, from the disorder of random variability, can nature achieve the beauty of adaptation without intelligent innovation. Intervention. Darwin's fundamental contributions to propose a mechanism natural selection and no one had thoroughly explored before. In providing his theory of evolution by natural selection, Darwin was explicit on the failure of Paley's arguments from design, how that laws of natural selection has been discovered, no more decide in the variability of organic being and in the action of natural selection, that in the course that the wind blows. The old argument of design in nature as given by Paley, which formerly seemed to be to me so conclusive, false. Now that the law of natural selection has been discovered, we can no longer argue that, for instance, the beautiful hinge of bivalve shell must have been made by an intelligent being like the hinge of a door or by a man. So Paley devoted one chapter of natural theology to the design of human body and